Welcome to today's Explainer. We're jumping right in, and today we're going to embark on a journey that will fundamentally shift how you understand the mechanical and physical definition of life. We aren't just looking at what living things do. We're going way deeper. We're examining the architectural rules of existence itself. We're going to strip away the assumptions we normally make about biology and look at the absolute foundation of what separates a living organism from the cold, inanimate universe.
So let me ask you something that might sound a bit absurd at first. Are you made of living matter or just organized matter? We tend to carry around this deeply ingrained misconception that life is made up of some sort of magical, vital substance, right? Like we look at a rock and we look at a rabbit, and we just assume the rabbit is constructed from special living atoms. But as you'll see throughout this explainer, life isn't a special type of matter at all. Instead, life is an active, continuous rebellion against inanimate chaos. It's a state of being that literally has to be constantly fought for. And that brings us to a massive foundational truth. Life is not a substance. It is a mode of organization. Think about it. If you were to break down your body, the exact same carbon atoms that make up your cells can also be found in the mud in your garden, the air you breathe out, and the lunch you just ate. The difference between you and the mud isn't the physical material itself. The difference is entirely in how those materials are meticulously organized, historically constrained, and constantly maintained. A living body is way less like a static statue and much, much more like a continuous, highly regulated process.
Section 1, the candle-flame paradox. And this brilliantly illustrates the problem with trying to define life too simply. Let's look at a false biological protagonist over on the left side, the non-living candle flame. If you argue that life is just metabolism, well, a flame consumes fuel. It transforms energy. It maintains a physical structure for a while. It responds to the environment, and it can even grow and spread like wildfire. It mimics so many traits we normally associate with biology. But then compare that to the actual biological systems on the right. Living systems possess historical memory. They actually contain instructions for making successors. They have incredibly complex internal self-correcting mechanisms to stop themselves from just burning out into smoke. A flame is just chemistry in motion. An organism? That is chemistry organized as a continuous lineage. Section 2. Resisting inanimate chaos. If biological life isn't just a chemical reaction burning through fuel, what exactly is it? Well, the crucial point is that a living cell acts as an accountant of improbabilities. I absolutely love this concept. The universe constantly pulls toward entropy, towards energy and matter dispersing and becoming totally disordered. But the cell maintains a highly improbable, beautifully structured internal state. How? It doesn't break the laws of physics. It just acts as a really shrewd accountant managing a thermodynamic budget. It uses free energy to do the useful work of maintaining its internal order, and it literally pays for that local order by increasing thermodynamic disorder or entropy somewhere else. It keeps its books with molecular receipts. Now, what's really interesting about this slide is how that boundary actually works in practice. To keep from decaying, a biological boundary actively takes in energy-rich matter and essential signals from its environment. It uses those raw materials to catalyze reactions, repair its own structure, and grow. But to balance those thermodynamic books we just talked about, it has to export waste products and heat back out into the universe. Life is an open exchange. It only survives by constantly actively negotiating with the environment across this physical boundary. Section 3. Comparing biological systems. With that thermodynamic bargain in mind, let's break this down into a step-by-step guide to the actual architecture of life. Step 1. You absolutely need a boundary to separate the self from the chaotic non-self. Step 2 is metabolism, that controlled flow of energy we just covered. Step 3 is regulation, or homeostasis, the ability to maintain internal conditions when the outside world gets rough. And step 4 is information and lineage, meaning the entity carries genetic memory and participates in reproduction. This is the necessary progression you have to go through to transform from a simple chemical reaction into a fully autonomous biological unit.
Okay, let's dive into this heat map, because this fundamentally changes how we categorize existence. Being alive isn't just a simple yes or no checkbox, it's a gradient. Look down at the bottom rows. Our old friend the flame scores a solid 0.6 on metabolism, while a highly ordered crystal scores zeros almost across the board. Neither of them has biological information or reproduction. But a mule, on the other hand, scores perfectly on boundary, metabolism, and regulation.
However, because it's sterile, it scores a 0 on reproduction. Yet, nobody in their right mind would say a mule isn't a living organism. This heat map shows us that biology is really about organized dependency and varying degrees of autonomy, not just solitary perfection. Let's look even closer at some of these borderline suspects. A virus is a great example. It has a genome, heredity, and evolution. It possesses biological information, but it completely lacks independent metabolism. It literally has to hijack a host cell to do the heavy lifting. A prion is even simpler. It has templated structural propagation, meaning it can spread its shape, but it completely lacks a genome and a cellular boundary. Neither of those are fully autonomous living systems. But then look at the sterile worker ant. It has metabolism and organization, yet it lacks direct individual reproduction. But we definitely still consider the ant alive, because the reproduction criterion in biology operates at the level of the evolutionary lineage, not just the isolated individual.
Section 4. Chemistry with a memory. So biological systems are fundamentally just chemical reactions, but they're chemical reactions that have been granted the incredible gift of historical constraint and evolutionary memory. And because of that historical memory, life behaves so differently than a simple chemistry experiment in a beaker. In a standard lab, you mix things and often wait for a reaction to reach equilibrium, a state of total stillness and balance. But in biology, a cell at total global equilibrium is an obituary. It's dead. Living chemistry requires a highly disciplined, regulated equality of opposing tendencies, homeostasis, that must be constantly fueled by energy to avoid ever reaching that final still equilibrium of death.
Let's move to and see how this builds across completely different scales of life. Look at the compact, single-celled E. coli bacteria on the top. It's a brilliant example of streamlined autonomy. It handles its boundary, metabolism, regulation, and information all in one tiny, efficient package. Now compare that to the complex eukaryotic HeLa cells on the bottom. These show incredible internal specialization, with a nucleus, a cytoskeleton, and distinct compartments. Both of these entities are solving the exact same thermodynamic equations of life we've been discussing, but they do it using entirely different historical architectures. It just goes to show how organized chemistry can scale up to staggering, mind-blowing complexity. But, that complexity isn't a free-for-all. Living systems don't just explore all conceivable forms. They are beautifully constrained by a strict set of rules. Physical rules, like how heat and fluids move. Chemical rules that govern catalysis and binding. Developmental rules based on what an organism actually inherited from its ancestors. Historical rules limiting the variations even available to them. And of course, ecological rules dictating what actually survives out there in the wild. These constraints aren't a defect of biology. They are literally the grammar for the language of life. They're what turn random chemical possibility into actual biological order. Which leaves us with one final, pretty sobering question to ponder. What happens to this biological bargain when the energy finally stops flowing and the chemical memory fades? Well, the boundary fails, the thermodynamic debt comes due, and all that highly organized matter returns to the inanimate chaos of the universe. Our organized existence is a continuous act of rebellion against natural disorder. It's a magnificent performance of chemistry with a memory, but it only lasts exactly as long as the energy flows. Keep that in mind the next time you look at a flame, a tiny bacterium, or even yourself in the mirror. You aren't just static matter, you're an ongoing event. Thank you so much for joining me for this explainer, and keep questioning the mechanics of the world around you.